Dr. Alessio Lerose. He's currently at the University of Geneva, and Alessio got his PhD in statistical physics at the International School of Advanced Studies at Trieste, Italy. And his research interests are condensed matter theory, quantum simulations, and quantum many-body physics. Welcome, Alessio. Over to you.
Thank you very much. Okay, so first of all, I had serious problems with Wi-Fi during Bruno's talk. I hope it won't really happen again during my talk. So hope this will be smooth. And first of all, I want to join the previous speakers in thanking the organizers for putting this interesting workshop together. It's very nice to participate. And okay, so what I'm gonna tell you about today is some work that I've been doing in Geneva, together with mainly together with Michael Sonner. So please tell me if you see my pointer and see correctly my slides and hear me. So it's work done mainly with Michael Sonner and Dimitri Abanin in Geneva, based on these works that were published last year. Plus, I will also mention some ongoing progress that we're making in collaboration with Julian Sonner and Lorenzo Piroli and other people. Okay, so okay. So the basic problem we consider is the following. So we want to consider time evolution of a quantum many-body system extended. So let me consider a very specific and simple setup, just a quantum spin chain initialized in some unentangled product state with all spins pointing in the same direction. And we want to consider its time evolution under the action of some local Hamiltonian. So in this, the time evolution is, so the system is isolated from its environment, so it's globally coherent, but and the spins become more and more entangled as time progresses. But when we look at what we are actually interested in, so typically dynamics of observables which are local, which are supported on a finite region of this system, then this evolution typically looks incoherent, so perhaps noisy and dissipative. Okay, and the typical expectation for a generic quantum many-body system is that there will be a short transient over which the local observables will reach some steady value, which is compatible with thermal equilibrium. So the way this is usually phrased is that the system is able to behave, to serve as a thermal bath for itself. So to thermalize its own local subsystems. Okay, so behave as a bath. Conversely, of course, it's very interesting to understand, well, first of all, to understand why and how this happens, and also to understand the limitations of this occurrence. So understand what are the systems for which this doesn't happen, and because this system allow to circumvent constraints of equilibrium and perhaps realize non-equilibrium phases of matter. Okay, so this is the setup, and how do we do this? So how do we follow the dynamics, the relaxation dynamics of local observables? Well, naively, this seems like a very hard problem, and the reason is the following. The reason is we want to describe time evolution of reduced density matrix of a finite subsystem embedded in this extended large many-body system, and in order to do so, we have to compute the time-evolved many-body wave function, and then take trace out all the degrees of freedom outside our local region. But this is very hard, no? Because the time-evolved many-body wave function is a very complicated object. It's massively entangled, and it's even impossible to write it down after a transient, no? because of the growth of quantum entanglement. Okay, but then on the other hand, this is sort of paradoxical, because we know that at least in many cases, it is believed and expected that the system reaches thermal equilibrium, where the late time state of the system is also simple. And the reason for this is that most of the information encoded in the time-evolved many-body wave function is actually, so we are trying to describe all possible non-local correlations, right? But if we are only interested in local observables, most of this information is useless. So most of the entanglement of the degrees of freedom in our finite system with all degrees of freedom of the faraway degrees of freedom is actually amounts to building up the local entropy, right? But the system locally forgets quantum information that was in the initial state and just relaxes to thermal equilibrium. So it is at least conceivable that you can sort of circumvent this entanglement barrier and describe the and be able to describe dynamics of local observables without this difficulty. Okay, so this is the hope, and the way we want to approach this is essentially realizing that we can treat our finite subsystem as an open quantum system. So as a system, and viewing the rest of the other degrees of freedom outside this subsystem as an environment for it. So taking literally this notion of system acting as a bath for itself. Okay, and the minimum amount of information we have to retain to evolve the local reduced density matrix of our subsystem is the so-called Feynman-Vernon influence function. So let me just quickly remind you what is this concept. So this concept was actually introduced by Feynman long ago. It's you can learn about it in famous book by Feynman and Hibbs back in 1963, and this was introduced by Feynman and Vernon to describe dynamics of open quantum systems in contact with a bath by essentially giving up the description of the bath and just describe an effective evolution for the subsystem. And the celebrated application of this formalism was done by Leggett and co-workers on their famous study of dissipative two-state problem, so a two-level system in contact with a bath of harmonic oscillators. And also more recently, it was studied in other contexts like in nano devices.
Alessio,
so yes.
So how does this framework, Feynman-Vernon framework, is compared with the standard CPTP maps or the open quantum systems like GKLS equations or cross representations used in the standard open?
I will mention this later.
Sure, thank you.
I'll explain it. Thank you. Okay, so let me just explain briefly how it works. The idea is that we are interested only in observables or correlation functions happening only in the subsystem. So we're not trying to describe any observable pertaining to the bath, to the environment. Okay, so we express time evolution of the system plus bath using a path integral that was also invented by Feynman, and then we essentially incorporate all the effect of the bath, so all the summation over all trajectories of the bath in a functional of the subsystem trajectory. So we express time evolution as a path integral over the trajectories of the system only, okay, weighted by the local action of the system plus some weight that incorporates all the effect of the bath. And this weight arises from summing over all trajectories of the bath. So it's expressed in the last line below. And some intuition on what this functional is can be obtained if you think for a moment that for example, the system is linearly coupled to the bath, as Feynman considered. So imagine this interaction action of the system and bath is linear. Then this summation is nothing but a sort of Fourier transform of the action of the bath. Okay, so it's a sort of generating functional of the quantum noise exerted by the bath on the system. So this doesn't depend at all on the dynamics of the subsystem. It's a property of the bath and on how the bath is coupled to the system. Okay, so this can be done, of course, for harmonic oscillators because path integral is quadratic, and still it's a non-trivial piece of theoretical physics to understand what happens to, for example, to a spin coupled to this bath. This is the work by Leggett and others. Okay, so what we are trying to do here is essentially to use this formalism to study dynamics of local observables in extended quantum many-body systems. So essentially, in a word, what we aim for, what we want to do, is essentially to transform our original many-body problem in an effective few-body problem involving only the degrees of freedom contained in the finite region S. But this few-body problem will contain essentially self-interaction of this subsystem with itself non-locally in time. Okay, this is what we're trying. So we're trying to eliminate space from the problem and obtain some effective non-local in time in description. Okay, so how do we do this in practice? Well, essentially, let me go back to the original, to the very first, so to the beginning of my talk, so to the very first prototypical example. So some spin chain initialized in some simple initial state. So the state becomes entangled as time proceeds. What we do, we express, so we select a finite region. So for example, let me consider spin P, position P along the chain that I call S. And then we describe time evolution with a path integral from time 0 to time t. Okay, and then we sum overall trajectories of all the spins to the left and to the right of our spin P. Okay, and the result of this summation is nothing but Feynman-Vernon influence functional expressing the influence of all spins on spin P, of all the system on spin P. Okay, so this is a very complicated problem in general because, of course, this is not a bath of harmonic oscillators, so it seems a bit hopeless. But one crucial observation you can make is that in translational invariant one-dimensional problems, at least, or in general in problems in tree-like geometries, what you can do, you can formulate an exact self-consistency equation for the influence function. And the reason is actually very simple. The reason is that if you imagine you have computed the influence functional acting on spin at position P, okay, and now you want to essentially incorporate spin P into the environment and compute the resulting influence functional on the next spin at position P plus 1, okay. So by translational invariance, the result of this operation should produce the same influence functional that you had before, okay. So this act of introducing an extra spin, incorporating an extra spin into the environment translates into an equation that your influence functional has to obey. Okay, so let me be even more concrete. So how do you attempt to do this in practice? Well, what you can do, you can, as is standard in path integral approaches, you discretize time, so you trotterize time evolution. So you end up, imagine you have, just for simplicity, local interaction, so interaction between nearest neighbors. So you end up with some effective quantum circuit description of your dynamics, similar to what we have seen in previous talks. Okay, so this sort of brickwork structure expressed in so you can view your path integral as the application of a quantum circuit, or equivalently, you can view this as a tensor network. So as this graphical illustration of your circuit can be interpreted as a tensor network of subsequent application of repeated application of many unitary gates, which you can view as tensors. Okay, and now how do you want to compute influence functionals? Well, what we said, we single out spin at position P, and we trace out all the spins to the left and to the right of spin P. So what we do essentially, this act of tracing out is expressed by this graphical illustration below, where I'm using essentially the same notation that Peter, Tomas, and Bruno introduced, so I won't repeat it. And this is the graphical representation of your essentially of your influence function. Okay, so this red shaded object, the summation of all indices contained in these red shaded objects is nothing but the influence functional acting from the left and from the right on your spin P. And by inserting observables along the dynamics of spin P, you can essentially reconstruct all possible observables and temporal correlations happening locally in your finite region. Okay, and then essentially what the act of performing the path integral is nothing but the acting of contracting this tensor network, and you can think of this contraction as something that proceeds along space. So that's something that as a contraction acting on the space direction. And after you did that, you end up with some big complicated tensors, which are represented by these pink shaded objects, one from the left and one from the right, which incorporates all the influence of the bath on your spin P. So in this approach, you see that you haven't tried. So you have given up once and for all the possibility to describe non-local correlations. So to describe the time evolved wave function of the system at the price of introducing. So you have to deal with local temporal correlations. So you traded non-local spatial correlations with non-local in time correlations, so locally in space but non-local in time correlations. Okay, so whether this is advantageous or not depends on the problem at hand, and this is what I'm going to discuss. Okay, so this is the main idea, and the exact self-consistency equation that I described before is nothing but the act of applying a sort of transfer matrix acting along the space direction to your influence functional acting, describing the influence of the bath up to a certain spin. And this produces the influence functional acting on the next spin, but this, by translational invariance, this should give the same as before. So this takes the form of an eigenvector equation for this transfer matrix, which is sort of similar to what Bruno has described for spectral statistics, but actually here the boundary conditions are different, and this changes the spectral property of this transfer matrix. But on the other hand, the main idea, I guess, it's similar. All right. So okay, so before I go on, let me, still in terms of formalism, so it's legitimate to wonder if this object has some physical interpretation, right? Because it's some mathematical construction that allows you to incorporate, to essentially to keep track of local evolution of the system. So it allows you to characterize dynamics of local observables, and in particular the character of dynamics, for example, thermalizing versus localized and so on. But it turns out you can also give a direct physical interpretation to this object. And the idea is the following. So imagine I want to keep track of, essentially to store the correlations incorporated in the influence function. And what I do, essentially, I take a collection of ancilla qubits or qubits, depending on your problem, in maximally entangled pairs. And what I do, essentially, I at first time step, I have my system interact with my ancillary systems, and then at second time step, I have them interact with my second pair, and so on. So I use a different pair of ancillary qubits for each time step, and at the very end, so after further time step, after all time steps, essentially I trace out my my bath, my environment, and I end up with some. Sorry, I end up with some quantum state of my ancillary qubits, and this quantum many-body state essentially is nothing but, you can view this explicitly in the graphical illustration here. This is nothing but a quantum many-body state that incorporates all temporal correlations of the encoded in the influence function. So to remember this, I think it's useful to go back to this famous quote by Einstein in the slide here. So essentially, it's a quantum many-body state that incorporates temporal correlations. Okay, and you can view this essentially as in quantum information language. You can view this as the sort of Choi matrix of partially concatenated quantum channels, where the concatenation refers to the environment degrees of freedom. And also there is a nicer trick that avoids using non-local operations that you can find in this recent archive by Hippolyte and others. Okay, so you can wonder now, it's legitimate to wonder if this is an arbitrary state, or if the fact that of encoding temporal correlations constrains you more. And turns out actually this is the case. So influence function is not an arbitrary state. It's a state that it's a many-body density matrix that is further constrained by the fact of incorporating temporal correlation. For example, is constrained by causality, and this is something we're trying to characterize at the moment. Okay, so this is the formalism. So question is now, what can you get out of this formalism, right? And first observation you can make is that actually is to look for exact solutions. So is to look for limits of where a quantum many-body system behaves in a very simple way and exerts a very simple influence on its local parts. And the simplest action you can think of is actually that of essentially the strongest possible action of a quantum bath on a subsystem, which is just perfectly measuring spins attached to the bath at all time steps. So what we call here a perfect dephaser. Okay, so this mathematically this is expressed by an influence function that just kills every interference in all possible trajectories. So it just imposes that the forward and backward trajectories of the subsystem are just imposed to be the same at all time steps. So it just kills all off diagonal matrix elements at all time steps. So the question is now, is there, can you imagine, can you exhibit a quantum many-body system that behaves like that? And turns out actually this is possible. This happens, for example, in a prototypical quantum circuit or prototypical periodically driven system, which is the Kick-Teasing chain. So just an Ising chain with a chain quantum spin chain with Ising in nearest neighbor interactions and some kicks in some direction periodically in time. And now when you fine tune the kick strength, the transverse kick strength, and the interaction to some value, which turn out to be very special for a reason I'm going to say in a moment, this turns out that this simple influence function, this simple perfect dephasing influence function exactly solves the self-consistency equation. So it is actually, it expresses the induced dynamics of the system on its local parts. Okay, and this actually, I think it's remarkable because it essentially tells you that the action of a system on its own subsystems is perfectly Markovian. So this function is completely factorized in time. So it means that it exerts a kind of action on its subsystem that is independent at each time step. And this is strange because essentially, well, normally you need more. No, you need more to in the open quantum system theory. You need some separation of time scales, for example, in order to have a Born-Markov approximation. Here there is no such thing. So it's just a remarkable property of this fine-tuned Floquet systems. Okay, and turns out that these values that were actually known to be special, it's the values that make your Kick-Teasing chain self-dual. So essentially a version of this dual unitary circuit that previous speakers spoke about. And actually, it turns out that if you the most general, essentially, if you want your circuit to be deterministic, meaning no ensemble averaging in your gates, and you want this property to hold, essentially the general property you have to ask for your circuit to produce this perfect dephasing or strongest version, which is perfect depolarizing property, is exactly this dual unitary condition that for the Kick-Teasing chain this was proposed in this paper by Achille et al. Some years ago, but was more recently exploited very much by Bruno, that we just heard in a series of papers where it was used to essentially compute very non-trivial quantities of chaotic many-body systems like entanglement growth and spectral statistics and these kind of things, correlation functions. And this, of course, we're hearing many things about this in this workshop. Okay, so this dual unitarity essentially is what allows you to prove that certain circuits produce this perfect dephasing action on their local subsystems. Now, it turns out that this is not, you can view this property as the property of a deterministic circuit to produce the same quantum noise on its own subsystems as a fully random circuit. So it turns out that if you take a fully random version of this circuit, of this brickwork circuit, where gates are extracted at random, or either fully at random or at random in space and constant in time with a large local Hilbert space dimension, this produces the same influence function. So you can formulate this property of dual unitary circuits as the property of producing classical white noise on their own subsystem, which is the same kind of noise that you would find in completely random circuits. Now you can wonder if some degree of ensemble averaging is necessary at all, no? Because here we don't have ensemble averaging over gates, but we have ensemble averaging over initial states, right? Because we're considering infinite temperature initial states of the environment. It turns out no, actually this problem was solved in this nice paper by Lorenzo Piroli and Bruno Bertini and others, where essentially you can show that there are pure states, so no ensemble averaging at all in the initial states, that produce the same property. So that allows you to essentially allows you to contract this tensor network and produce this perfect dephasing property. Okay. So this is a convenient starting point if you want to analyze generic properties of influence functionals, because, as I said, this is a this is a point where the influence function takes a very simple form. It's just a fully factorized. It's a product state in time. It's fully factorized in time. Okay. So this also means that if you view this as a quantum many-body state, as I mentioned before, this is just a, well, this is a maximally mixed state, but it's just the identity density matrix. It's completely factorized for different time steps. And now you can introduce the notion of some entanglement in this quantum many-body state, which is not really, doesn't really pertain to quantum information notion of entanglement. It's just a measure of how much correlated is this object in time. Okay, and so if you essentially, this is related to the possibility of describing this object as a matrix product operator, essentially. So as a of how well you can factorize it in time, in the time direction. So it's related also to the efficiency of computing this object numerically. So what you can imagine essentially is that when you detune your parameters away from these fine-tuned points where the influence function is exactly solvable and takes this perfect dephasing form, well, these points will have low temporal entanglement, essentially, because just by continuity, essentially, because you're close to a point where you have zero entanglement. And this allows you to essentially to perform efficient numerical computations using matrix product states and matrix product operators. So essentially, the idea is that the most straightforward idea to do this is essentially to express your influence function as a matrix product state ansatz, and then you can essentially try to iterate your transfer matrix, which has naturally a matrix product operator form, and look for the essentially so-called quote unquote steady state of the action of this transfer matrix. Okay, this is something that actually was done much before in the tensor network community, in a famous paper by Banyurs et al., where essentially this was exploited to, well, essentially to seek the best pattern to construct a tensor network that allows you to describe dynamics. Okay, so what we find essentially most appealing in this approach is that the influence function knows everything about the dynamics of local observables. So in particular, it should allow you to characterize dynamical phases. So for example, it knows whether the system is going to thermalize, so it's going to locally forget the memory of the initial condition and just reach thermal equilibrium, or if it fails to do so, and retain some information about the initial state. So it plays a role, if you wish, it plays a role for non-equilibrium dynamics that is similar to the role of ground states for equilibrium physics. So it's the properties of this fictitious state characterize the basic dynamical properties of the system. And in particular, you can hope that this classification of dynamics can be done using properties of temporal entanglement. So essentially the structural correlations incorporated in this object. And this is what we have tried to do, and what I will briefly sketch in the remaining part of the talk. So I will talk about essentially how to compute non-Markovian corrections to this Markovian relaxation corresponding to perfect dephaser points, and to how to characterize phase structure of many-body system using temporal entanglement. So we've also done some work. Well, we began to do some work on disordered system and how to characterize the many-body localized phase and the many-body localization transition using this formalism that has its own advantages, but I won't talk about this in this talk. Okay, so briefly, I want to discuss this. So what you can do essentially when you imagine, well, let's step back and go to the perfect dephasing property, which you can realize by tuning your model parameters to this, for example, to these dual unitary circuits. So what the perfect dephasing influence function does essentially is to enforce pairing of local trajectories. So it essentially forces trajectories of a spin of a system attached to this environment, to this bath, to be equal at all time steps, to the forward and the backward trajectory to be equal at all time steps. So it kills local interference. Okay. Now this translates into a weight for your local trajectories that is 1 for when these trajectories are paired and 0 otherwise. Now, if you imagine to detune your parameters away from this solvable point, now, of course, these trajectories where with portions of forward and backward trajectories that differ will not be completely suppressed as they were in the perfect dephasing point, in the exactly solvable point. They will just be strongly penalized. So you can imagine to describe your influence functional as a sort of statistical mechanical action for portions of trajectory that are unpaired. Okay, so what are called essentially blips in the work by Leggett on spin boson model, on these Caldera-Leggett models back then. Okay, so essentially what you can study and what you can try to characterize is the fact that the influence function of a generic ergodic system, so not a fully maximally chaotic system, but just so you want to characterize what is the structure, sort of the robust structure when you detune away from this solvable points. You can try to describe this, and what you can show is that this can be described as a sort of weakly interacting gas of blips. Okay. Now, of course, I don't have time to explain this because it would take me too much time. But essentially, I want to convince you that this is not only conceptually nice, but it's also practically useful for computations. For example, you can imagine to use this approach to compute the relaxation rate of an impurity immersed in your strongly chaotic spin chain. And essentially, imagine you put at some position on your spin chain, you put some impurity which is slower, so it has some internal dynamics, some kick dynamics, which is slower than the rest of the system. This kick essentially acts as a sort of chemical potential in this statistical mechanics viewpoint. This acts as a sort of chemical potential for blips, so it allows you to go to a regime where the blip gas is dilute, and in this regime, it turns out you can compute well, semi-analytically essentially the relaxation rate of this impurity. So which is defined by this quantity, this persistence probability, if you initialize it in the up state and look for the probability to find it up at a later time.
So
okay, so this decays exponentially. Yes.
Hi. So is sort of 5 more minutes before the question answers okay sufficient?
Yeah, I'll try to go faster.
Sure.
So okay, so this relaxation rate essentially, this is you have your exact result, which is computed at the perfectly phasing point, plus some correction that you can compute by resumming all the blips essentially. And this turns out to match very well the numerics when you're close to this dual unit, to this self-dual point. So there is a range in which this approximation, this non-interacting blip approximation that you use to resum the blip weights work well. When you go far away, you see some discrepancy, which you can attribute to interactions between blips. Now, I think it would be interesting to essentially compare this approach to other recently developed approach to corrections to solvable many-body chaos. One is what we heard this morning by Tomasz, but also other approaches that you see here, that I reported here. Okay, and in the remaining 5 minutes, I want to sketch this how you can get some mileage from the influence functional to characterize the phase structure using temporal entanglement. Now, the starting point here is a different solvable point, which is essentially the kick teasing chain in the integrable limit. So in the limit where there is no longitudinal component of the kick, and this can be mapped to free fermions. Okay, so in this case, you can compute the influence functional exactly because the dynamics of the bath is essentially can be mapped to free fermions. So you can perform the path integral and arrive at a formula for your influence function. And in this case, you can essentially show analytically that your your influence function is quasi-local in time. So it has some effective interactions of the subsystem with itself in time, which decay. And they decay with a specific power law, which is in this case t to the minus 3/2. And this allows you also to prove that, at least in this case, to prove that the influence function satisfies an area law scaling of temporal entanglement, so it can be efficiently represented as a matrix product state. Okay, so this is the thing, and this also turns out this applies. So this is not specific of the Kick-Teasing chain. It's not specific of the infinite temperature ensemble of the environment. So it actually applies to, more generally, to families of models that are that have this property of being mappable to free fermions, and for general non-equilibrium initial states. Okay, so essentially, the way you can understand this property, the property of having low entanglement is the following. So imagine I have an environment which is finite, has some finite length L, and I want to understand what are the correlations, the temporal correlations incorporated in the influence function. And essentially, in this case, where the dynamics in the environment can be understood in terms of exact quasi-particles, what you can do essentially is you can count how many ways correlations between the past and the future can be brought by traveling quasi-particles in the environment. And when your environment is finite, this entanglement can be brought by quasi-particles that are created in the past, gets reflected on the spatial boundary of the environment, and go back to the future across this bipartition in time. Okay, so this generates a sort of a volume law of your temporal entanglement, but the coefficient of this volume law depends on the geometry of the problem. So it depends on the size of the environment. And if you do this calculation on varying the size of the environment, you find that essentially there is a sort of barrier shape. So for smaller environments, this temporal entanglement grows, but then it goes down, and in the thermodynamic limit, it goes to a finite value, which is nothing but this area law that I described before. And this you can account for by this quasi-particle picture. Now, in the limit of, as I said, in the limit of infinite environments, the only entanglement you can generate across this cut in time is created by infinitely slow quasi-particles. So by quasi-particle traveling at zero velocity. And this is the origin of this advantage, if you wish. So of the fact that your influence function is low entangled, and so it can be efficiently represented. And this is because essentially you have traced out the environment, so you have given up the possibility to describe non-local correlations, as I explained before.
Now, Alessio, can I ask?
Please.
So the initial state that you're taking is what for this picture?
In this case, it's a Gaussian state, if you wish, a general Gaussian state, so a state made up of pairs.
Okay, but then I could imagine that typically when you have the states made of pairs, the pairs of correlated quasi-particles are propagating with velocities with different sign. But I can cook up some states where I have the pair that propagates in the same direction. So in this way, I would generate some correlations between past and future, also in the thermodynamic limit. No?
Yes, I think so. Yes, we haven't done that, but I think if you create such a state, I think you could cook up a state, an influence function that has volume law entanglement.
Thanks.
And of course, this becomes important when you have a more complicated state that are non-Gaussian, but then you can more easily realize this situation. But yeah, no, I agree. It's strictly within this assumption, which is, as you know very well, it's what happens when you, for example, you do a global quench or things like that. Okay, so just because I don't have much time, I want to mention briefly that more recently we are considering the effect of integrable interaction. So essentially, a situation where you still have exact quasi-particles, but these quasi-particles interact in a non-trivial way. And turns out that in some cases you can show that, in particular in the dual unitary case, we can show that you still have sublinear scaling of this temporal entanglement, but which becomes logarithmic in this case. This is work that we're doing with Lorenzo Piroli and Giacomo Giudice and Giuliano Giudice. I don't have much time to speak about that. I just want to mention briefly a couple of things. So one thing is that you can, as I said, you can characterize phase structure by looking at temporal entanglement. In particular, when you cross a phase transition, you can for example, the buildup of an edge mode, which is characteristic of a topologically different phase from across the phase transition. This shows up in the form of temporal correlations incorporated in the influence function. In particular, this function that describes effective interactions in time becomes a function that doesn't decay to zero. And this is the hallmark of this long time persistence of edge coherence in your problem. And this is related to the physics of strong zero modes, and also appears in temporal entanglement, because turns out you have a finite jump as you cross the phase transition in the saturated value of your temporal entanglement. And yeah, so you can study essentially this temporal entanglement throughout the phase diagram, and you find this finite jump, as I said, and it turns out there is a scaling form of the value of saturated temporal entanglement as you approach the phase transition point, and in particular in proximity to the self-dual point, which is the crossing point in this Kick-Teasing chain diagram, which I'm showing here. It's the crossing point of the two critical lines. Here, essentially, the value at self-dual point is zero, as I mentioned before. But it turns out that as you approach this point, the scaling of temporal entanglement behaves in a peculiar way. So in particular, it becomes slower, and so it saturates to a value that doesn't depend on the parameter, so that approaches asymptotically a constant, but this saturation becomes slower and slower as you approach the self-dual point. And again, here you can find a scaling form for this approach. This of course complicates the analysis, because it means that when you approach the solvable point, you have non-trivial behavior that becomes slower and slower. So numerically, it becomes harder and harder to understand what is the asymptotic behavior at long times. Okay, and you can also study integrability breaking in this setting. So since this integrable manifold provides a convenient starting point for studying temporal entanglement, then you can imagine to break integrability by adding to stay within the family of Kick-Teasing chain. You can add a longitudinal field, and then turns out that depending on the phase where you are, you can have either behavior that even for quite strong integrability breaking, you still see sort of saturation of your temporal entanglement. Or if you go to, for example, to the topologically non-trivial phase where you have these edge modes, here you find a much faster, still parametrically slow, but an asymptotic growth of your temporal entanglement, which we don't fully understand. I must say it could be related to the appearance of more edge modes tied to the boundary, but this is something to be understood better. And okay, maybe I will skip this, and I will leave you with this. I hope I'm on time. I will leave you with this essentially conclusions and open challenges in this temporal, essentially trying to understand quantum many-body dynamics using temporal entanglement scaling. In particular, one important question is to understand whether this sublinear scaling that we find, which seems to give you an advantage for numerics, is something that is generic or not. This is something we don't know at the moment, and would be very, very interesting to understand. So briefly, intuition we have some control limits suggest yes, but numerics is so far not conclusive, partly because as I said, when you approach controlled limits, things become slower. And more importantly, we don't have a physical picture for unlike the scaling of spatial entanglement, which is more well understood. In this case, we don't have a physical picture for the generic case. And a related question is temporal entanglement entropy the appropriate measure for the complexity of an influence function. So in particular, this is related to the statement that MPS is matrix polar state the most natural correct ansatz for an influence function. This also is something we don't fully understand at the moment. So there are some indications that this could be the case. For example, influence function is the extremum eigenvector of an MPO transfer matrix, so which is similar to what happens for ground state. So this seems to be promising. On the other hand, you have, even for non-interacting system, you have this algebraic decay correlation, which are enough. In the non-interacting case, this is enough to prove slow scaling of temporal entanglement. In general, this seems to be not enough. So the exponent is not fast enough. And there are these slowdown close to solvable points. And finally, you can show that truncation of small singular values in this MPO representation can be harmful. You can show this with simple example as we found in this paper, and also we're trying to essentially to characterize this aspect at the moment. Okay, so I'm done. So I'm happy to answer questions if there are any.
Thank you, Alessio. Yeah, so actually we are already exceeded time. Maybe a quick question, and then you can take it after the next talk with Alessio. Any quick question?
Probably I should answer the question that I was asked before during the talk. So the relation to this CPTP map. Actually, yes, it turns out influence function is a way to define a CPTP map, if you wish. So if you define evolution from time 1 to time 2, so from a certain time to another time, then the map, the quantum channel defined by the action of your influence function of above traced out at the final time defines a CPTP map. But in general, the influence function is much more than that, because you don't trace out the buff at all time steps. So it describes a process with many times. So it's like incorporating all possible CPTP maps.
Hey, what I wanted to know is the path information in usual CPTP formalism is in some way encoded in Sudarshan Cross operator. So where in the Feynman-Vernal approach this path information is kind of encoded?
Well, from the influence function, you can define all possible CPTP maps for the evolution of your subsystem. But as I said, there is more information than that, because you have access not only to dynamics of observables at a given time, which would be defined by this CPTP map, this collection of CPTP maps, but you also have access to all possible temporal correlations. So all possible statistics of fluctuations in time of your observables, which is not encoded in a single CPTP map.
Okay, thank you.
So there is more information.
I thank Alessio again. And is Sarang here?
Yeah, I'm here.
Yeah, Sarang. Welcome, Sarang.